reactions too. In this experiment, we accurately weighed around 0.1 grams of the unknown chloride and put it into a 250 centimeters cubed beaker to know exactly the mass of the sample so that we could calculate the amount of chloride and identify the unknown later on. This was then dissolved in approximately 100 centimeters cubed of water and 3 centimeters cubed of 6 molar hydrochloric acid, or nitric acid rather. Water is used here to dissolve the chloride salts, releasing chloride ions, and nitric acid keeps the solution acidic, preventing unwanted precipitation of other silver compounds like silver carbonate or sulfate. We then slowly added 0.1 molar silver nitrate solution until silver chloride began to coagulate. Then we added a further 5 centimeters cubed of silver nitrate, making sure no more than 25 centimeters cubed total was added. The silver is added, obviously, so that the silver ions can react with the chloride ions to form solid silver chloride, which precipitates, and adding slight excess at the end ensures all chloride ions are fully precipitated. We then heated it carefully for 10 minutes without boiling, as heating helps the silver chloride particles coagulate and settle, improving the quality and ease of filtration. It was then left to cool, as it stabilizes the precipitate and reduces the chance of losing material during filtration. And then we filtered the reaction, making sure to wash with dilute nitric acid to make sure that it removes any impurities and soluble salts without dissolving the silver chloride. We then took the wash solution and added a few drops of 2 molar hydrochloric acid. This checks if any chloride ions remain in the wash liquid. Formation of a precipitate would indicate that chloride is still present, so further washing is necessary to ensure all chloride is still solid. It is in the solid precipitate. We then put the precipitate in the oven to dry in order to remove moisture, so we could get more accurate mass measurements to calculate the moles of silver chloride. Once we got our boat, our weighing boat, from the oven, we weighed it and we got 1.3029 grams, which we then subtracted the weight of the weighing boat from that to get just the mass of the silver chloride, which we got as 0.2329 grams. We then use this in combination with silver chloride's molar mass to calculate its moles, which we got as 1.625 times 10 to the power of minus 3. Because silver chloride has the same number of moles as silver and chlorine, the moles of silver chloride are also the moles of chlorine ions. We can then use this with chlorine's molar mass to calculate the mass of chlorine, which we got as 0.0576 grams, and which we can then subtract from the original mass of the unknown chloride to get just the mass of the cation, which we got as 0.0424 grams. And we use again the moles from earlier to calculate the molar mass of the cation, which we got as 26. So we identified the possible, or we said the possible identity of the cation might be magnesium, as it is the closest to 26 with a molar mass of 24.03. You can then see our predictions here with the ionic equations on the side, including spectator ions. Most of these we predicted would have white precipitate, or most of the white precipitates we see on the table we predicted would occur because one of the products would be insoluble. For example, zinc carbonate is insoluble, so it creates a white precipitate visible. And using that table, we then compared it to the observations table on the blind trials, and we determined that A was barium nitrate, B was lead nitrate, C was potassium iodide, and D was sodium carbonate, E was zinc nitrate, and F was magnesium sulfate.